We're going to do a couple examples together, and then you're going to have a lot of time to work today. So you'll be able to ask questions on anything from yesterday, and then today we're going to look at Hess's law and some thermochemical equations, which is essentially using stoic and delta H in order to go between like grams and moles and kilojoules and joules. Now for number one, this was a question similar to some of the beginning questions on the calorimetry practice from yesterday. So for number one, we have calcium chloride being dissolved in water. And it says the temperature of the solution increases. So my focus, what I'm focusing on, is the CaCl2. This is my system. Right, so the calcium chloride is my system. We're going to talk more about solution calorimetry on Monday, but when we create a solution, we dissolve a solid in water, we're making a solution. The solution is considered the surroundings. So the solution that's being created, the styrofoam cups, the thermometer, that is all part of the surroundings. So solution calorimetry, when it's asking about exo and endothermic, we have to think about things a little bit differently. Oh, I just answered part A. So system is CaCl2. Surroundings is literally everything else. So the surroundings would be the styrofoam cup, the solution, the thermometer, the cardboard lid. But the system is CaCl2. So when it's asking about being exothermic or endothermic, remember that that is based on the system. So we need to ask ourselves, what does the system have to do in order for the surroundings to increase in terms of temperature? So if we think about the system is the calcium chloride. The solution temperature increases. So the temperature of the surroundings increases. So you have to think, what does the system have to do in terms of heat? It's either going to absorb or release for the surroundings temperature to increase. So if calcium chloride is the system, and I want the surroundings temperature to increase, that's like when you're around a fire, you're the surroundings, your temperature is increasing. So that is exothermic. So in order for the surroundings temperature to increase, calcium chloride has to release heat because you're measuring the temperature of the surroundings. So if you're releasing heat, part B is exothermic. So that's looking at solution calorimetry. Like I said, we're going to look at that a lot more on Monday into like Tuesday of next week as well. And then number two, so this is kind of going off of a question that we looked at yesterday in one of the examples. If the molar heat capacity of a compound with the formula C2H6SO is 88 joules per mole Kelvin, what is the specific heat in joules per gram Kelvin? So notice the only difference is moles to grams. So I'm going to write out my molar heat capacity. 88.0 joules per mole times Kelvin. And I want to convert that mole part to grams. So I want to cancel out moles. So I'm going to put it on the top so that it cancels. And I want to put grams in its place. So if we look at our periodic table, carbon is 12.01 plus 6 times 1.008 plus 32.06 plus 16. The molar mass of this is 78.128 grams per mole. So the molar mass is always for 1 mole, 78.128 0.128 grams for 1 mole. It's always 1 mole, whether it's on top or bottom, 1 goes in front of moles. So now moles cancel. So when I multiply and I divide, 88 divided by our answer, 1.13. So joules is on top, Kelvin and grams is on bottom. So it takes 88 joules to heat 1 mole of this substance by 1 Kelvin. But when we switch the units, we find that it takes 1.13 joules to heat 1 gram by 1 Kelvin. So again, there's a difference between molar heat capacity and specific heat, and the difference is whether you're heating 1 mole of something or 1 gram of something. Any questions on this? All right, just a quick reminder that we have a weekly review this week. It's been up on Google Classroom. After today, because today we're looking at Hess's law, you should be good to answer those questions. They're all multiple choice, but it's going to look at thermochem, so everything from this week. Okay, so the next thing I want to look at is thermochemical equations. And you had a separate example within the notes on thermochemical equations. So thermochemical equations were on page 7. So thermochemical equations were at the top of page 7, and there was an example from the video that used thermochemical equations, but I just want to look at another example. So wherever you might have space, you can, or just anywhere, really. You could add this, or you could just kind of work through it on like scrap paper too. So a thermochemical equation, if we break this down, thermo means heat, and then chemical, we have our formulas. So thermochemical equation is an equation. It's a balanced equation, has coefficients, but it also includes delta H. And so when we see a thermochemical equation, like in the example on page 7, we have a balanced equation and then we have a delta H value off to the side. When we have a thermochemical equation, that allows us to use heat like it were a reactant or a product. So it lets us go between moles of a substance and kilojoules of heat. We just treat that delta H like it would be part of a mole ratio. So an example that I pulled to put up here and work through, the complete combustion of ethanol, which is C2H5OH, to form water and carbon dioxide releases 1,235 kilojoules of heat per mole of ethanol. So number 1, write the balanced thermochemical equation for this reaction. Okay, so really it's a balanced equation and we're going to include delta H off to the side. So ethanol, C2H5OH. We don't have to worry about states of matter. Unless it specifies states of matter, we don't have to worry about it. Now the only thing it doesn't give us here is what else we need when we have a combustion reaction. What's the other reactant that we always need if it's combustion? O2. Produces CO2 and H2O. Now we'll balance this in a second. Then we're also going to include a delta H value off to the side. So if we balance this, we have 2 C's, save O for the end. 2 C's, 6 H's, 6 H's. So there's 4 plus 3, there's 7 oxygens. I have 1 here, so what would I need to put in front of O2? 3. There's our balanced thermochemical equation, or there's our balanced equation, I should say. So now we just need to fill in delta H. If it releases 1,235 kilojoules, what's the sign for delta H? Negative. It releases. That's exothermic. So negative 1,235 kilojoules per mole. There's our balanced thermochemical equation. It's a balanced equation with delta H off to the side. When we have delta H like this, we can go through stoichiometry problems. So number 2 says if 2.5 moles of ethanol react, how much heat is released? Now some people can look at this and kind of think about it in their head, but I'm going to show you how we set it up. So my given information is 2.5 moles of ethanol. It's my given information. My given information is already in moles, so I don't have to worry about converting to moles. Now it's asking me to go from moles of a substance to heat. I can use this balanced equation, just like I would with stoich. What I can do is that I can put moles of ethanol on the bottom, right, almost like a mole ratio. But instead of moles of something on the top, I can use kilojoules. Because I can use this delta H as part of our mole ratio. So my coefficient for ethanol is 1. So for 1 mole of ethanol that is combusted, 1,235 kilojoules are released. So we're treating it just like it were part of a mole ratio. Instead of moles over moles, we have moles and kilojoules, and we use coefficients and our value of delta H. So 2.5 times negative 1,235, negative 3,087.5 kilojoules. Now here's a quick thing as we're working through thermochemistry. Because the problem already says how much heat is released, this released already tells us the number should be negative. So if you actually would just put 3,087.5, you would still get that point, because it's already saying that it's released. If you have a problem that says something about give the magnitude, that just means it wants the number. You don't have to worry about a sign. Because a lot of times the problem will already say how much is released or is absorbed. That also does, if you want to include the sign, tells you what it should be. So the idea of thermochemical equations is just that we can use delta H as part of a mole ratio to go through stoich. Questions on this before we look at Hess's law?
Was this the one where you flip the equation, or is that Hess's law?
That's Hess's law.
Okay.
Yes. Yes. So that will bring us into Hess's law. So there were a lot of questions on the video about Hess's law. A lot of it was looking at how do we cancel, how do we flip, what happens to the signs. And so we're going to go through an example looking at Hess's law, and then you're going to have lots of time to practice with Hess's law. Once you see how Hess's law works, then you're like, oh, okay. And people like when they have Hess's law because it's just manipulating equations. So it's kind of thinking about us having a system of equations. Now, the definition is that if we can add 2 or more thermochemical equations, right? So there's the thermochemical equation. We have a balanced equation with a delta H value. We can add 2 or more equations to produce a final equation for the overall reaction. Then we add up the delta H values to get the overall delta H. So all we're doing in Hess's law is that we are manipulating given equations and manipulating the delta H values in order to find a new overall equation. And based on how we manipulate the equations, we add them all up. We add up all of our delta H values. So we're going to look at example number 6. So this is in the notes packet. Example number 6 is on page 11. So I have some part of the in-class examples. Page 11 of the notes is this example. So, kind of going along with the questions, how do I know when to use calorimetry? How do I know when to use Hess's law? If you see that you have multiple equations given with delta H's and it says find this new equation, that immediately tells you Hess's law. When you see a setup of a system of equations like this, that means we're going to be using Hess's law. So here's what I start with when I'm looking at Hess's law. Start by looking at this new equation that we need to get. So I need to manipulate these top three equations to get this new equation down here. Now you're going to notice that you'll have some reactants that are always present in like all of these. Oxygen, hydrogen. So you don't want to necessarily use hydrogen and oxygen as a starting point. I always say use something like carbon because I noticed that only one equation has just carbon in it. Right? Use like C2H2. Only this one has C2H2. So I'm going to start just by focusing on carbon. I need 2 moles of carbon as a reactant. So I'm going to find the equation. I'm going to number these equations 1, 2, and 3. So as we talk about the equations, I could say equation 1 or equation 2 or equation 3. So I have 3 equations up here. The first thing I'm going to focus on is getting 2 carbons, 2 moles of carbon. Which of these equations has just solid carbon in it? 2. Right? It has solid carbon as a reactant. That's good, because I want carbon as a reactant. So it's already on the right side. I should say it's already on the correct side. But I need 2 moles of it. Right now I only have 1 mole. Right? There's no coefficient, so it's 1. So if I need 2 moles, I need to multiply this entire equation by 2. You can't just multiply carbon. It's like in math. If you want to multiply one variable by 2, you have to multiply the whole thing. If I multiply this entire reaction by 2, I also need to multiply my delta H by 2. So I'm going to now rewrite this over here off to the side so you can see how I cancel and how I add everything up. I need to put it in a different color. So I'm going to have 2 carbon plus 2 O2 yields 2 CO2. And then the delta H will be negative 393.5 times 2, negative 787. I just literally multiplied everything by 2 and wrote it here. Okay? So now I got carbon in the right place. I'm going to not worry about hydrogen yet, just because it could potentially be in multiple places. I'm going to focus on C2H2 next. I need 1 mole of C2H2 to be a product. In which of these equations do you see C2H2? 1. C2H2 is right here. But it's a reactant. I don't want it as a reactant, I want it as a product. So we have to flip this equation. When I flip the equation, that puts the reactants as the products as the reactants. So instead of this now being exothermic, if I flip the reaction, I flip the sign. So instead of it releasing heat, it now has to absorb heat. Now I have just 1 mole, which is what I want, so I don't have to do anything else to the equation. You could potentially do multiple things to a single equation. If you have to, you could flip an equation, you could multiply it by 2. You could flip an equation and multiply by 1/2. Right? So you could do multiple things to one equation. So I'll go ahead and rewrite this. And what I'm going to try to do is line up the arrows so when it comes time to cancel, all of our arrows are as lined up as possible. So I'm going to kind of work backwards. C2H2 plus 5 halves O2. So again, our delta H, we just flipped the sign, so plus 1299.6. So then, lastly, I want to find hydrogen. I want to make sure that hydrogen, 1 mole of H2 is a reactant. So the only equation I haven't manipulated yet is equation 3. Does equation 3 have 1 mole of H2 as a reactant? Yeah, I don't have to do anything to this equation. It's good. So I'm just going to rewrite it down here for when I cancel. Again, I don't have to do anything to this equation because 1 mole of H2 is already a reactant. H2 gas. H2O liquid. So since I didn't do anything to the equation, I'm not going to do anything to delta H. So now, before I add these up, I'm going to cancel out anything that is both on the left of the arrows and on the right of the arrows. So what we need to do is we need to look and see what is the same on the left and on the right. So I look and see, okay, well there's 2 CO2s on the right here, 2 CO2 gases on the left here. So I can cancel the CO2s out. There are 2 of each, so they both can cancel. Sometimes you might see that only one of them will cancel. Just like if you had 2x on one side and x on the other, only one of the x's can cancel. What else could I potentially cancel that's on the left and on the right? So if we look here, there's no carbon on this side. It has to be the exact same. So like solid carbon, no solid carbon over here. 2 O2s. Well, I have 5 halves O2. Notice here I have 2 oxygens and 1 half oxygen. 2 plus 1 half is 5 halves. So I have 2.5 oxygens. 5 halves is 2.5 oxygens. So oxygens, all of the oxygens will cancel. In the example in the video, only half of an oxygen canceled, because that's all that was available. Anything else that's on both sides? H2O. Now that should leave us with what it wanted in this equation. So we have 2 carbons, 1 H2, 1 C2H2. So when I add all of these equations up, I get 2 carbons plus H2 yields C2H2. I just add everything up. So think about this being like adding 3 systems of equations together. Which means to get our delta H, we just add all of these values together. So we add negative 787 plus 1299.6 plus negative 285.9. Don't forget your negatives. For delta H, I got 226.7 kilojoules. So, based on this value of delta H, it's positive. What type of process overall is this new equation? Is it exo or endothermic? Endo, right? It's positive. Delta H is positive, it has to absorb heat. This is endothermic. So, that is looking at Hess's law. We can manipulate equations, we can flip it, we can multiply, we can divide. And the whole point of Hess's law is to use these known equations with delta H values to come up with this new equation by manipulating and then adding together the delta H's. Right, so now you guys are going to have some time. You're going to just have some time to actually work. So in the notes packet going on in the practice, there is Hess's Law practice. It's pages 14 and 15, and I gave you guys lots of space, so there's only actually 5 problems, but I gave you lots of space to be able to work through. Now, you might not need the space. I rewrote everything here, but you'll notice on some of my answer keys, no, I rewrote them for everybody to see. But when I work through problems on my own, I don't always rewrite everything like I did here. You'll see that a lot of times I say flip times 2, and then kind of just put in my answers. So Hess's Law, pages 14 and 15, the answer key is here. It's also here on the board. And then page 16 ties in calorimetry and Hess's Law together. 16 is just 4 questions. 2 multiple choice, 1 calorimetry calculation, and 1 Hess's Law calculation. Just a way to kind of tie everything together. Answer key I have linked also up here on the board. And then after working through the practice, so you have lots of time to work together, to ask questions. Then you can, if you need to go back to any of the practice from yesterday, check answers, ask questions. You can work on the post-lab if you need to. Remember, that's due Monday. We will have a pre-lab due Monday. The handout is already posted in Google Classroom. I'm hoping we can do that lab in person. That's the plan. And so that's looking more at calorimetry, or you can also work on mastering. So you have different things that you can work on after. Remember, AP exam sign up, all that information, there's the Google Sheet that's on the stream of Google Classroom. I updated it yesterday at 10:45. So if you're signed up in total registration, if you are registered in AP Classroom, you have to make sure to choose yes for like that you're taking the test. So I have that updated in the Google Sheet as well. And then just remember, Westinghouse, people sign up on the Google form. Remember, I need the release form as well, so I can send that to Westinghouse tomorrow. I do have some up here. It's like you sign it, a parent signs it, and I know I won't see you tomorrow, so if you take it home, get it signed, you can just take a picture and email it to me. That way I have it. I just need it digitally to send to Westinghouse. And then SNHS applications are due a week from today. So I'll leave this up on the board. It's really just time for you to practice. You can move around, you can work with other people. The answer keys are up on the board, so you can feel free to take pictures as well if you